Hello, everyone, and welcome back to our series on hypercompositional algebra. In episode 1, we introduced the idea of replacing classical operations with a set-valued operation. And we saw why this generalization is useful in mathematics and its applications. Today, we move to one of the most fundamental structures in hypercompositional algebra, the hypergroup. And this hypergroup that we'll consider it during this episode is Marta's hypergroup. We will learn its formal definition, understand how to verify whether a given structure is a hypergroup, and we will study also finite and infinite examples. Let's begin. Imagine multiplying two numbers and obtaining not one answer, but several correct answers. At first, this sounds impossible because classical algebra teaches us that every operation has exactly one outcome. However, many mathematical models naturally allow multiple possible outcomes. So instead of saying A with the operation B gives C, we have the right now to say A gives, let's say, X, Y, Z. Required. Hypergroups provide one of the earliest and most important examples of this idea. By the end of this video, you will be able to define a hypergroup formally, distinguish between finite and infinite hypergroups, read and interpret a hyperoperation table, and verify whether a structure satisfies the hypergroup axioms. Here we give the definition of hypergroupoid formally. We are starting with H, a non-empty set. And we are defining a hyperoperation from the Cartesian product of H with itself to power star of H. So here, what's power star of H? Power star of H, it is all subsets of H without the empty set. So it's the set of all subset of H without the empty set. We call this one as a binary hyperoperation, and the couple H with circ, we call it as hypergroupoid. This reminds us of the definition of groupoid, but instead of having binary hyperoperation, we have binary operation, and the binary from the Cartesian product H cross H to H. Now, what if we are finding the hyperoperation between two sets? We take A in A, B in capital B, and we take the union of all of them. And this will be a circle. Let's give now a concrete example. So let's define this hyperoperation. I will call it star. This is A, and this is B, and this is A, and this is B. Let's say that I will put here B. Now, we said before that it should be a non-empty set, right? Here I put B. Because it's a singleton, I have the right to put it as a singleton, and for simplicity, I can keep it just as B. This one I will put, let's say, AB. This one, let's say I will put A, and this one, for example, we will put also AB. So if I take here H, the set containing AB, star is a hyperoperation on it, and H star is a hypergroupoid. Now, why it is a hypergroupoid? If you look at any two elements in H and we take X star Y, do we have an empty in any case here? None of these is empty. Plus, every one of these is a subset of H. So in this way, H star is a hypergroupoid. So a hypergroupoid is simply a non-empty set together with a hyperoperation. Nothing is required at this stage. We haven't imposed any algebraic properties. Associativity may fail, identity may not exist, reproduction may not hold. So a hypergroupoid is therefore the most general hyperstructure. The next step is to impose additional conditions. The first condition that we will consider is the associativity. In case the hyperoperation is associative, we will arrive at a semi-hypergroup. And in case the reproduction axiom hold, we will arrive at a quasi-hypergroup. And in case both of them occur, means that it is associative and it is a quasi-hypergroup or the reproduction axiom, we will get a hypergroup. Let's look at this diagram. Of course, every hypergroup is a hypergroupoid. Because the hypergroup, it should be hypergroupoid first, satisfying the reproduction axiom and the associativity. Now, also, if you look here in this diagram, we're seeing that the group, every group is a hypergroup. Why do you think that every group is a hypergroup? Let's start with a group. G dot is a group. Why is it a hypergroup? If you look at AB, which is in the Cartesian product of G with itself, it goes to A dot. Now, if you allow this one to be a singleton, this one, of course, it satisfies the reproduction axiom as a group, right? Plus, is associative. So it is a quasi-group. It means that it's a quasi-hypergroup. It's associative. It means that it's a semi-group and therefore a semi-hypergroup, and therefore it is a hypergroup. So basically, the hypergroup is a generalization of a group. Let's recall. A hypergroup is a hypergroupoid in which we have associativity and reproductivity. The associativity again is A round B round C equal to A round B round C, and reproductivity, it means that XH or AH is equal to HX equal to H. Now let's try to verify with concrete examples. So here we are starting with H, any non-empty set. And we are defining two hyperoperation. The first hyperoperation I will highlight and we call it as total hypergroup. And the second hyperoperation, I will highlight it in blue, and we call it as the biset hypergroup. Let's start with the green one. We are saying here that A star B is equal to H. First, let's look at it. Is it a hypergroupoid? So A star B, if you look, it's not empty, and it's equal to H, which is subset of H. So it belongs to pair star of H. So the first thing, this one is a hypergroupoid. Now we need to check whether it's associative or not. For associativity, our aim is to find A star B star C and to find A star B then star C. If we look at A star B star C, it is all A star X with X in B star C. But A star X, if we look at this one that is here, it's equal to H. We're done with this one. Now what do we need to find? We need to find A star B star C. This one, it's equal to X star C with X in H. And this one again, X star C, by definition, it's H. So the associativity law will hold. We proved that it's a semi-hypergroup. Now the next step, we need to prove that it is a quasi-hypergroup. To prove that it's a quasi-hypergroup, our aim is to show that X star H, or if you want to say A star H, to show that X star H or A star H, for example, is equal to H, and it's equal to H star A. I will do this one. A X, the union, such that X belongs to H. But A star X, it's H. Union of H is H. And of course, H star A is done in the same way. Now, to make sure that you understood, I highly encourage you to try to prove that the biset hypergroup is a hypergroup. So the blue hyperoperation will reproduce, again, a hypergroup. Like finite groups, finite hypergroups, we can represent them by means of Cayley's table. Here's an example. This one with this hyperoperation is a hypergroup. Now, first of all, let's try to read this Cayley's table. First of all, is it a hypergroupoid? When we ask, is it a hypergroupoid, it means that is there any of the parts in the table that is empty? The answer is no. Is there any cell in the table that is not a subset of H? We have H, we have AB, we have AC, all of them are subset of H. So first of all, this one is a hypergroupoid. The next thing, let's check the quasi-hypergroup, the reproduction axiom. The reproduction axiom, how does it work? We can look at the rows or at the columns. Look at the rows first. And the union of the cells in the columns, is it H or not? The first column, the union is H. The second, the union is H. And the third, the union is H. In this way, when we look at the column, as if we are checking H star X is equal to H. Now, let's look at the rows. What's the union in the rows? In the rows, when we look at the rows, it means that we are checking whether X star H is equal to H. The rows are satisfied, the columns are satisfied. It means that the reproduction axiom holds, and it is a quasi-hypergroup. Now, to check the semi-hypergroup, we need to check all possible combination of the elements. You can, for practice, try some of them. So far, we gave finite examples. Now we'll give infinite example. This example that I took is one of the most important books about hypergroups, specifically its polygroups and related systems. Starting with a group, we can define a hyperoperation, the subgroup generated by xy. I will give a particular example when G is the group of integers under addition. So basically, we're starting with the group C plus, and we are taking the hyperoperation A with B is the subgroup generated by A, which is basically all linear combination of A and B. Of course, xy here belong to C. Now, let's look at A round B. Is it a subset of C? So this is hypergroupoid. And of course, it's not empty. Why it's not empty? Because A belongs to A round B. Why? Because we can write A as linear combination of A and B. So we prove that it's a hypergroupoid. Now, the next step, we need also to prove associativity. And the associativity, it's simple here. I will leave it for you as a simple exercise. And we will prove also the quasi-hypergroup. Quasi-hypergroup, it means that we need to prove that A round C is equal to C round A equal to C. Now, I will prove one of them. Why? Because if you look at Z round A or A round C, they are equal to each other. Now, to prove that A round C is equal to Z, we need to show first that A round C is a subset of Z, and already we showed why, because it's a hypergroupoid. And we need to show that Z is a subset of A round C. Now, to show that Z is a subset of A round C means that every element in Z should be in A round C. So let's take an element in C. Our aim is to show that this element is in A round C. It means that it can be written as linear combination of A with something else. So B, isn't it equal to A times 0 plus B times 1? So it's where it's in A round B, which is subset of A round C. So we proved that it's a quasi-hypergroup, and the associativity, you can prove it later on. Let's summarize the key ideas from today's lesson. A hypergroup is built from a hypergroupoid by adding associativity and the reproduction axiom. And the operation or the hyperoperation, it will always produce non-empty subsets. And of course, hypergroups can be finite or infinite. Before moving to the next episode, try answering this question. And why did I put this question? Because this was the motivation beyond or behind introducing hypergroups by Marty. We said in the first episode that if H is a normal subgroup of G, we will arrive at a group. And if it's not a normal subgroup, we'll arrive at a hypergroup. So as an exercise to practice, you can prove that it's a hypergroup. And you can also take a particular example and try to see how is this hypergroup will be formed. Thank you for watching episode 2 of our Hypercompositional Algebra series. And please, if there is any particular thing that you would like to share, ask about, you can leave it in the comments. And of course, you can find me on LinkedIn by just scanning the QR code. Have a great day and see you in the next episode.